right. Gavin, are you there? Nope, you're not there. Well, join when you join, I guess. OMG. I knew that was the grade you were going to make before you made it. I was in the kitchen mumbling to myself, I'd be surprised if she didn't make that grade. Do we? Well, it wasn't just faith. It was, I knew that you were getting it really well and that you were working hard. Those two things together usually mean that kind of grade. And I also knew the test was easy if you understood what you were doing, which you did. So, you know, I knew what was going to happen. Look, there's a Gavin. Well, actually, there's a Gavin's avatar. We can't see Gavin's face. He likes to hide. Can you hear me, Gavin?
Yeah, I can hear you. It's a little scratchy, but I can make it out.
All right. A little scratchy, but you can make it out. It's because my computer's trying to do too many things at once. All right. We are on chapter 5. Does that sound right to everybody? This unit, I say this every time, and sometimes people listen to me and sometimes people don't listen to me. So, you know, you should be the person that listens to me, but we'll see what happens. This unit is extremely vocabulary heavy, like really, really. And it is I would, I say this all the time, but I would make flashcards for this unit. And I would get a study buddy and get somebody to help you study and whatever else. Because there's a lot of words and they sound a lot alike. We've got things like circumcenter and orthocenter and altitudes and medians and bisectors and then other kinds of bisectors and all kinds of stuff. And you need, and each one has a little theorem that goes along with it. And so the I have said this before many times as well, but you can start studying for the test after you do the first lesson. And I would. It's not necessarily that this chapter is harder than any of the other ones. It's not really. The math is pretty straightforward. Some of them on some of it's really easy, but there's a lot to remember in this unit. So I would start just kind of the memorization studying like today. Make sense? Okay. What numbers did we do on this lesson? Two through 30. Oh, 10 through 30. And then 38, because I had to give you a proof, because I'm so nice. It's good for you. All right, number 10 is 9. Number 12 is 10. Number 14 is 16. Number 16 is a picture with a bunch of medians drawn on it. We can do more than that if we need to. 18 is segment CF. 20 is segment DA and DB. 22 is 17. 24 is 4. 26 is 30. 28 is 13.1. 30 is 28.5. And 38 is a proof. We'll almost certainly look at the proof, but do we have questions before we look at the proof? $28. Let's do it. All right. 28, we've got a big old triangle. That we've got this one and that one. And we've got 33 degrees. This side length is 13, 10.9. This is 28.5. Oh, I probably didn't draw this quite right. These are not what I thought they were. This is 14.9. Yeah, these are, yeah, okay. So it says that P, which this is P, and we've got A, B, C, D, and E, and also F. And it says that point P is the incenter of triangle AEC. Find the measures below. Okay, so what does incenter mean? Which one was that? You should be able to look at your notes for the video, right? Because that was in there. Even if you don't have it memorized yet, you do need to start working on that, but which one is the incenter? Point of concurrency between which ones? It's an Aiden. You gotta go take a test, buddy. How you doing this morning? Good? All right, grab your test and you can go take it. I think it is this one. I think correctly. There you go. If you have any questions, send up a flare. Okay. Incenter is the point of concurrency between what? Is it the angle bisectors? Oh yeah, it is. It is the angle bisectors. Yes, it is in fact the angle bisectors, which is good because if it wasn't, this problem would be impossible. Point P is the point of concurrency between the angle bisectors. That is true. That is a true sentence. Great. And for 28, we're looking for the measure of segment DE. So this one. Okay. So it is, so these are the angle bisectors, which means this is this and this is this, etc., right? That's what's going on. Yes? Easy peasy. What else does it mean? What does the incenter theorem say? So, despite what I drew, all of these, like distance to the sides, are equal. So this is congruent to this is congruent to this. True enough. Okay, so that's vaguely useful, but not directly, right? Because it was like something over here, and then that would give us something useful. Well, we need to find what this distance is first. How could we do that? We've got right triangles, right? So if we know two sides of a right triangle, we can find the third. So is there any of the triangles that we know two of the sides to? The answer is yes. Y'all just got to find it. What? PAB, absolutely. Good naming. Good job. Yeah, it is triangle PAB. This guy right here. We have we have two of its sides. It's true enough. So we have this side and this side and this side. So if we pop this triangle out, he looks like this. And he's got this side and this side. So us knowing two sides on a right triangle lets us use what to solve for the third? This is an end of Algebra 1 topic. Do we not remember or don't want to say? If we don't remember, then I got you. Okay, so I'm going to take it as we don't remember or don't remember well enough to be confident. So let's get this happening. I don't know why I drew a D, because I did. Okay. If we have a right triangle, Pythagorean theorem says that a squared plus b squared equals c squared. Okay. So we can use that. Now, the question is which letters are which? Which ones are A and B? We don't care which ones are A and B, believe it or not. Those can be switched around, right? All right, when we switch these around, commutative property says that's fine. All we need to know is which one is C. So which one is C? It is 13. It is the one, it is the longest leg. It's also, this is important for a problem like this, because you look at this, you're like, especially how I drew it, which one's longest? It's also the one across in the 90. He has a name. Does anybody remember what that side is called? That longest side in the right triangle? What? No, it's not Haley. His name is the hypotenuse. Hypotenuse. Right? So we can set up the equation 10.9 squared plus a squared equals 13 squared. All right, grab your handy dandy calculator and tell me what 10.9 squared is. $118.81. And what's 13 squared? $169. Now what would we do to solve for A? Subtract, easy peasy. So what's 169 minus 118.81? 50.19. Now, how do we get rid of that squared? What's the opposite of squaring something? It is square root, that's right. Now, I say this in geometry, I make a big deal about this. We will pretty much never use this fact in geometry, but I say it so that you will hopefully remember in Algebra 2. So technically, when we take the square root of both sides, we end up with plus or minus. So plus or minus whatever that is. What is that number? Square root of 50.19. You can go to the hundredths is probably fine. 7.08. Approximately equal to plus or minus 7.08. However, distance is always positive, so we just absolute value and throw out that minus. So when we square root both sides, we get plus or minus, but we don't need the minus because we're talking about distance. So this is about 7.08. Which means this is about 7.08, right? Because this point P is equidistant from all the sides. This would also be 7.08. We're looking for this one. So we have this side and this side, so what can we do again? The same thing. A squared plus B squared equals C squared, right? 7.08 squared. And if you leave this in your calculator, you can even get a more exact answer, right? You can just keep doing that. What's 7.08 squared? Oh, it's this. Right? 50.19 plus B squared equals, what's 14 squared? I don't know if anybody is on our internet stream today, but just so you know, I won't be able to respond to you because I have to have Discord open today, so I can't see you. So if you're there, welcome. I don't know you're there. 14.9 squared. All right, where's your calculator, bro? Did you forget it? Bruh. You don't need it as often. That's kind of true, but you do need it. All right, what's 14.9 squared, Mia? 222.01. And then we subtract. So B squared equals, what's 222.01 minus 50.19? You have a calculator on your phone, bro. What are you even doing with your life? What's happening right now? Oh, okay, good. And then we square root that, which would give us plus or minus, but we're looking for distance. So what's the square root of that? It's about 13.1. Which is the same number as the key says. We are in agreement. This is like a classic geometry problem. Nothing we did was really hard. You just gotta use the tools that you have and put them together, right? That's kind of the side of the brain that we're looking for, right? Is okay, well, this connects to this because of that thing, right? This kind of problem is kind of the practical point of proofs, right? The everyday type idea. What other questions do we have? from this lesson. I'm not letting you go early, so you may as well ask your questions. We can do the proof if y'all don't have any other that you know you want to look at. We can do the proof next. But sure. 14. What equation did you set up on 14? Mm-hmm. So you probably did some arithmetic mistake somewhere. Let's look at it real quick. Because they would be equal to each other, right? It's definitely true. So the equation you write for 14 is 4x minus 4 equals 2x plus 2, right? So what do we do to solve that? Okay, what do you mean? Okay, so what do you mean? You can't do that because of the equals. You got to move one to the other side. Is that what you meant? Okay, so what specifically are we going to do? Okay, how do you move it? Subtract it. True enough. He got to what I was asking him eventually. Okay, so we're going to subtract the 2x. So 4x minus 2x is what? 2x. Then what are we going to do? Add the 4. Then divide the 2. And we end up with x equals 3. Now, you'd be tempted to circle that and make that your answer, but that's not what it's asking for. Is that what you did? No? Okay. What did you do next? Okay, so what it's asking for is SW, and the triangle is just like that, exactly like that. No differences. And this one is 4x minus 4, and this one is 2x plus 2. And this is S, and this is W, and I don't even care what the other letters are, but this is R, and this is T. And the question asks to find the measure of SW. We've got x equals 3, so what do we need to do? Substitute it into either one, right? They're the same. Right, so we put it in up at the top. So 4 times 3 minus 4. What's 4 times 3? What? Nobody can hear you. 4 times 3 is 12, yes. What's 12 minus 4? It is 8. So if this one is 8, and this one is 8, what is SW? Yeah, 16. There you go. You may have just not finished it. That's possible. That's definitely possible. You got to make sure you look at what they're asking for. You said, oh, you said SW equals 3. Yeah, that's what I said. I said you probably just stopped there. Yeah, X does equal 3. You just didn't finish it. It's a scam. I know. You should have read. Reading's hard. Okay. Any other questions? All right, let's look at the proof. We have more practice. This is one of those where it's giving you one of the theorems that they give you in the book, and it's saying, here, prove that this is true, right? Which in the next lesson, we could just say, because of the in-center theorem, it's true. But we're being asked to prove the in-center theorem, so we can't do that. It's a scam, as Joe would say. Bruh. This is K. They give all kinds of helping triangles. It's not really helping triangles, it's just these full distances, which makes this problem particularly ugly. That's what I thought. I drew it good enough that it looks kind of like that would be the true thing. That, and then this one is up here. Then we got all kinds of letters. Big one is A, B, and C. What we're going to prove is the in-center is K. And then this is F, P, R, E, D, Q. Dairy Queen. Let's get a blizzard. All right, we are given that a couple of them are angle bisectors. Okay. Triangle ABC. So there's so many extra things I have to say. That is in fact a triangle, not masquerading as a hexagon or something. Angle bisectors. AD, BE, and CF. We are given KP is perpendicular to AB. We're given a lot of stuff. Maybe this proof won't be as long as I was afraid it was going to be. KQ is perpendicular to BC, and KR is perpendicular to AC. And we're supposed to prove the in-center theorem. So we're supposed to prove that KP equals the measure of KQ equals the measure of KR. Great. So, what should we do? That's funny. Since KP is what? That's kind of funny. This, is there another one before that that says something else? Oh, yeah. 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 That makes this proof exceptionally short. Okay, so what does the angle bisector theorem say? If you flip back in the book, it may be easier to read. Yeah, so if a point is on a bisector of an angle, we're given that these are bisectors. We're given that point K is on the bisector because it's one of the, wherever I'm pointing, where it's because that's in these guys, yeah? So that means that KP is congruent to KQ, right? KP, yeah. KP is congruent to KQ. It means that KQ is congruent to KR, and it means that KP is congruent to KR. So we can say that, right, on this next line, that each one is congruent to the other. And then they're all congruent to each other because of what? If A is congruent to B and B is congruent to C, then, yeah, so transitive property. And that's it. That's all this proof takes. You should put this one on the test. Yeah, so KP is congruent to KQ and KQ is congruent to KR, right? Because of the angle bisector theorem. Therefore, measure of KP equals the measure of KQ equals the measure of KR because of the transitive property. That's great. That's easy money. All right, how we doing? Thought that was going to take longer. Let's do another proof, I think. Yeah, let's do number 37. We have an upside down kite. More or less that. A, B, C, D, E. A, B, C, D, and E. I feel like this is going to be like, if we get to the kite lesson, this is going to be a one-step proof, but according to the book, this is a 19-step proof. Let's see what happens. We are given that CA is congruent to CB. CA is congruent congruent to CB. And we are given that AD is congruent to BD. AD, congruent to BD. We want to prove that C and D are on perpendicular bisectors of AB. So in order to be a perpendicular bisector, what are the things that have to be true? What is a perpendicular bisector? What is perpendicular? Cross 90 degrees. True enough. You even said it right. Good job. Half the time when I ask, what's perpendicular? Lines that cross. Yes, and? Good job. Cross it at 90 degrees. You had all the specificity required. True enough. So we've got to prove that, where is C and D? Okay, so we've got to prove that C and D are on perpendicular bisectors of A and B. So we've got to prove that these lines are perpendicular. Okay, what does bisector mean? A bisector, yeah, it's in the middle. That's true. So we've got to prove that this is congruent to this. Those are the things that we've got to prove. And all we know is that this is congruent to this and this is congruent to that. That's all we know. Sad. What should we do? What could we do? If you're not getting all the points when you're doing proofs, it may be that you need to write more instead of less. Because I never count off for having extra steps. I do count off if there's missing steps. Steps that are vital to add in there. So it might be that you need to write more things and not less. So what's something we could say about this picture? I know a direction we could go. What do y'all think? What kinds of shapes are up there? Let's do one of those Facebook posts. How many triangles are in this picture? There's more than 4. There's a lot more than 4. There's the 4 obvious ones. 1, 2, 3, 4. Where else are there triangles? Gavin, you still there?
I'm here.
All right. I'm glad you're here. You can play along at home. I said you can play along at home. You can also answer questions. It's allowed. All right, so we've got triangle AEC, triangle CEB, triangle AED, triangle DEB. Those are the ones we just said. Where's another triangle? BAC. We got this big top triangle, absolutely. Where's another triangle? ADB, that's the little bottom triangle. Little, not as little as these, right? All right, but yeah, we got this triangle. Where's another triangle? DAC, absolutely, and DCB, right? So if we could prove a couple triangles are congruent, we might be able to get more stuff, right? So which triangles might we be able to go for given what we're given? What are the 4 proofs for triangles? Side, 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 that's true. What else? Side, angle, side. What? Angle, angle, side, true. And then there's one more. Angle, side, angle. Okay. So if we could get one of those for one of the triangles, then we might be able to get some more stuff because of CPCTC, right? Okay, so you might think that, right? And so the top one, we've got this, but it's like only congruent to itself, and this one's only congruent to itself, right? Where do we have a couple of different types of tick marks? Yeah, the left and right. All right, so as we've got side, side, right? So we've already got side, side, so we could try to go for this one. Can we get the third side of ACD? It's congruent to the third side of BCD. What is the third side? Side, yeah, side, side, side is what we're going for. What is the third side of triangle ACD? We know AC, we know AD. What else what is the other side? What is his name? Not Bob. DB's over here. What? I know. That's why I'm trying to work. That's why I'm trying to work through this, because this is a thing that we should have known a long time ago and don't, which is fine, but we got to fix it. This is the triangle, right? Sides are side. We know that this side is called AC right here, right? This one is AD, right? What would this one be? CD, that's true. Right? So, and that's shared, right? So we know something that says if this one is the same as that one, then they're congruent, right? So we can say CD is congruent to CD. What is that called? What? Yes. Reflexive. Okay, so we've got that. So do we have one of these now? What? Yeah, we do. We've got side, 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 right? So we can say that triangle ACD is congruent to triangle BCD because of side, side, side. True enough. Which means that all of its corresponding parts are congruent, so we can probably get some angles. Right? Again, we're going for our goal. Our goal is to say, we need to say that this is congruent. I mean, let me give us a proving color. We'll use green as our proving color. So we're trying to prove that this is congruent to this, and this is a right angle. We need those two pieces of information. If we can get those two pieces of information, we're off to the races. We can't say either one of them yet, right? Because we need to know, we've got two big triangles. We need to get to some little triangles, which we can probably get to using what we've got. Okay? So What all can we say because those triangles are congruent? We can say all their parts are congruent, right? So what is the name of this angle right here? This one. What? No, AB is a what? Okay, so AD is a segment, right? We need 3 letters for it to be an angle, right? And the A has got to be in the middle, right? CAD. So this is angle CAD. What is this angle called? CBD. Angle CBD. And they're congruent because why? What says that all the parts are congruent? What is that called? Or what is it? What are the letters? No, CPCTC is what we're looking for. That is what it is. Corresponding parts of congruent triangles are congruent. So we can say that those are congruent. We can say that all the other angles are congruent as well. So angle CAD is congruent to angle CBD. We can also say that this angle is congruent to this angle. So what is this one called? ACB is the big one. But what is this little one here? Not C's got to be in the middle, so ACE, right? So this is angle ACE. What would this one be? BCE. Yeah. Angle BCE. So angle ACE is congruent to angle BCE. And then this last chunk is also congruent. So what is this angle called? ADE. And this one is called BDE, right? Angle BDE. Is congruent to angle BDE. All because of CPCTC. Okay. All right. Now what? Can we get any other triangles that are congruent? Probably. We've got an angle here. We've got sides here, right? So can we get side angle side up here? on these triangles. Yeah, we got to say CE is congruent to CE, right? Same as this, right? We could even probably, since it's the same thing and it's not relying on anything else, we could probably add that just right here. CE is congruent to CE. Still because of the reflexive property. And it didn't require anything else, right? It's just still true. And then triangle ACE is congruent to triangle BCE because of side angle side. Just dawned on me. I keep thinking, how are we going to get the perpendicular bit? But it just dawned on me where we're going to go eventually. We're going to go to the converse of the angle bisector theorem later. Actually, we could potentially go there now. So that tells us that the only thing that tells us that these triangles is that CAE is congruent to CBE, right? So these little ones up here are congruent. That's the only new thing that this gives us right here. Right? So angle AEC is congruent to angle BEC because of CPCTC, right? Corresponding parts of congruent triangles are congruent. So it tells us that just that, a little bit is also congruent. We can get the green part. We can get that these are also congruent, right? Oh, that is another new thing it tells us, right? AE is congruent to BE because of CPCTC, right? Because that's now the little triangles. That's useful, right? That's one of the two things we need. AE is congruent to BE. So we've got this green part. We just need to get this green part, and we're off to the races. Is CE a bisector, excuse me, of ACB? Yes, yes it is. True enough. Oh, I see what they did. I feel like there's an easier way than what they did. What theorems do we have? Converse of what you call it? Angle bisector. What does it say? Point interior angles equidistant in sides. Then it is the bisector of the angle. No, that's not it. No. If a point on the bisector of an angle is equidistant from the point, we proved that it is equidistant just now. We also know it's a bisector, right? There's not really a theorem that says that's a right angle that we have. The theorem would be something along the lines of a perpendicular line is the shortest distance between a point and a line. We don't really have that written, but that seems like a theorem we could probably write. I think that's probably good enough for this proof. This proof is way harder than one that would show up on a test, for sure. So what they do, we're about out of time. So something like that, what I just taught through would be like a better solution, but we'd have to have a theorem that said that, which could be written, probably is written. We just haven't been given it. What they do is they use the fact that all of the angles in a triangle add up to 180, and they do some substitution shenanigans to make a 180 divided by 2 equals 90, and 90 is a right angle because of the definition of right angle. That's what they do. They start grabbing some of these and do all of that and add all of these things in with that. I do think that our method reduced the number of steps, but not by a lot. So I think it's time to go. Y'all have a great day. Start making those flashcards today. I'm telling you, there's a lot of vocabulary, and it's a lot similar. In-center, ortho-center, circumcenter.